An integrating factor is a term added to the form of the terms in a function to make it integratable. In this video, we work with using integrating factors through inspection. Welcome to Engineering Math 5. Through visual analysis or by merely inspection, we determine an integrating factor to be multiplied to the differential equation to come up with its general solution. One might wonder how to inspect a differential equation, say the one given in the example. This can be answered by recalling the functions described in differential calculus. Recall two common procedures from differential calculus. First is the product rule. Say we are to expand the derivative of two variables x and y. Product rule states that the derivative will be the first with the derivative of the second plus the second variable multiplied by the derivative of the first, or that is x dy plus y dx. Another common rule is the quotient rule. In case we would like to expand the derivative of x all over y, we square the denominator and apply low d high less high d low in the numerator. So the derivative of x all over y will be y dx minus x dy all upon y squared. And interchanging the variables in the numerator and denominator will have the same analogy. Another common term from quotient rule is the derivative of the arctangent of x all over y, which would be taken as y dx minus x dy all upon x squared plus y squared. The same procedure is observed when the variables are interchanged. From the expanded forms, notice something common, that is having the binomial x dy plus or minus y dx and other combinations. These are the exact terms to be inspected in the differential equations later. Our goal is to multiply these terms by an integrating factor to revert them back to the standard form, which can easily be integrated. So note that the addition of terms will be sufficient to give d of xy, thus there is no need for an integrating factor, though one is required for the difference of the terms. So there are four options to restructure the difference of y dx and x dy. The first two will need to be divided by either y squared or x squared to revert back to the derivative of the ratio of the variables. The latter two will require to be divided by x squared plus y squared to take the form of the derivative of the arctangent of their ratios. Let's explain the concept further with some examples. Determine the general solution of the following differential equation using integrating factor by inspection. The function given as y dx plus the quantity x plus x cubed y squared dy is equal to 0. Start by distributing terms, coming up with y dx plus x dy plus x cubed y squared dy is equal to 0. It can be seen at this point that the first two terms are actually the target binomial, which can then be simplified as d of xy. The second term, however, has x cubed y squared with a derivative of y. So to conform with dy, we need to eliminate x cubed. And we can do that by multiplying our first integrating factor, 1 all over x cubed. By doing so, we arrive at the equation where x cubed from the second term can then be eliminated. But then, the first term is already affected with the appearance of x cubed. So multiply the second integrating factor, 1 all over y cubed, to the whole equation. It will make the equation 1 all over x cubed y cubed times the quantity y dx plus x dy plus the second term, which has y squared dy all over y cubed, is equal to 0, where we can cancel some more y's from the second term. Now we can simplify the equation as 1 all over xy cubed times derivative of xy plus dy all over y is equal to 0, which can also be written as xy raised to negative 3 derivative of xy plus dy all over y is equal to 0. And this function is ready to be integrated. So as not to get confused, let's simplify xy. If we let u equal to xy, the integral of u du is u squared all over 2. So the integral of the first term will be xy raised to negative 3 plus 1, and everything will be divided by negative 3 plus 1 or negative 2. The integral of dy all over y is ln y, and 0 will be c. To eliminate the denominator, we multiply the whole equation with the denominator negative 2 times xy squared. So it would be 1 minus 2 times xy squared ln of y is equal to 2c xy squared, which is similar with 1 equal to 2x squared y squared ln of cy. And that is the general solution for the equation. Moving on to our second example. Y times the quantity y cubed minus x times dx is equal to negative x times the quantity y cubed plus x times dy. Again, distribute the terms and arrange them in the standard form to bring about the equation equal to 0. Then extract out the common terms. It is a common technique to check variables with close exponents like y to the fourth power and y cubed, then x and x squared. After extracting the common terms, check which are the probable derivative outcomes, so the first term is an addition which can then be simplified as d of xy, while the second term is the difference of the terms. So we complete the second term by multiplying an integrating factor of 1 all over y squared, so the equation will be y cubed all over y squared times derivative of xy minus x times the quantity y dx minus x dy all upon y squared is equal to 0, where we can cancel y squared from the first term and have completed the second term. However, excess y and x are still with the terms, so multiply the second integrating factor, which is 1 all over y. By doing so, we can eliminate y from the first term and we can complete the coefficients of the second term. And we are now ready to integrate. Recall that if u is x all over y, the integral of u du is adding the exponent of u by 1 and dividing everything by the total number of exponents. So by simplifying, the integral of x all over y will be x squared upon 2y squared. So we get xy minus x squared all over 2y squared is equal to c. And to eliminate the denominator, we multiply the whole equation by 2y squared to have 2xy cubed minus x squared is equal to cy squared, or simplified further as x times the quantity 2y cubed minus x is equal to cy squared. The third example requires the general equation of y times the quantity x cubed minus y to the fifth power times dx minus x times the quantity x cubed plus y to the fifth power times dy is equal to 0. Similarly, start with distributing terms, making the equation x cubed times y dx minus y to the sixth power dx minus x to the fourth power dy minus x times y to the fifth power dy is equal to 0. Then group terms to have x cubed times the quantity of y dx minus x dy minus y to the fifth power times the quantity y dx plus x dy is equal to 0. Then check for exact differentials. In this case, the second term has y dx plus x dy, which can then be simplified as d of xy. Let's attempt to complete the differential on the first term by having the first integrating factor of 1 all over y squared. So the resulting equation will be x cubed times the quantity y dx minus x dy all upon y squared minus y to the fifth power all over y squared times the derivative of xy is equal to 0. At this point, we completed the exact differential in the first term, so we can write the equation as x cubed times derivative of x all over y minus y cubed times the derivative of xy is equal to 0. Note that there are still excess y and an incomplete coefficient of the first term with x cubed. So multiply the second integrating factor of 1 all over y cubed, which can transform the equation into the following. And we are ready to integrate. By integrating the first term, we would get 1/4 of x all over y to the fourth power, and the integral of d of xy is simply xy, and that of 0 would be c. The last step is to simplify the equation by eliminating the denominator, so multiply 4y to the fourth power to the whole equation to get x to the fourth power minus 4xy to the fifth power is equal to c times y to the fourth power, which can also be written as x times the quantity x cubed minus 4y to the fifth power is equal to cy to the fourth power. And this is the general solution for the differential equation. Let's check the last example with the differential equation of y times the quantity of x squared plus y squared minus 1 times dx plus x times the quantity of x squared plus y squared plus 1 times dy is equal to 0. First, distribute terms to simplify the structure of each term, and then group the terms most likely to give the common differential we are focusing on. Then transform the equation to exact differentials. At this point, there are two terms with the exact differential y dx plus x dy, so we can group them further to come up with the quantity of x squared plus y squared multiplied with the quantity of y dx plus x dy plus the quantity of x dy minus y dx. It is pretty clear at this point that the denominator required for y dx less x dy will be x squared plus y squared, as that is the coefficient of the first term. So multiply 1 all over x squared plus y squared as the integrating factor. After multiplying the integrating factor, it is noted that x squared plus y squared from the first term will cancel out, making the rest of the term readily integratable. The second term is also completed with the denominator, thus it can be simplified as d arctangent of y all over x. So by integrating the resulting equation, we arrive with xy for the first term and arctangent of y all over x for the second term, and c for 0.